Hello humans on this random planet called Earth, and welcome to my channel. Today we are back with part 2 of the Chemistry IA advice video and how to score a 7 on the Chemistry IA. And without further ado, let's just jump into it and continue this video because let's not waste more time.
Moving on to the process data table. This table basically includes your data after calculations. So up until now, you should not have presented any data with calculations, but only the exact results you measured. Keep in mind that for the Chemistry IA, sometimes it makes sense to present the process data first and then the sample calculation, but in many cases, you will kind of be presenting both as you go along. Here you can see several different process data tables as I go through the different stages of sample calculations. For my IA, this made sense because it had a logical flow to it, but you really need to see for your own IA how to structure the process data and the sample calculations because it does really vary quite a bit. Again, you want the independent variable on your y-axis and the dependent variable on your x-axis. Here you also include your standard deviation. Though some people included it in the raw data table, I would generally recommend that you include it in your process data, since in terms of communications, it makes more sense here, at least to me it does. The reason I say this is because I'm almost 100% certain that the standard deviation would be considered a type of process data, and in one of their subject reports, the IB stated that weaker candidates showed raw data together with process data in a way that made assessment quite challenging. Some very weak candidates only showed a graph as the only processing, while others reduced the processing to simple additions or subtractions. Note that you can't have standard deviations if you have less than 5 pieces of data. For example, if you have 5 trials for the 10% concentration and one of those trials is an outlier, you can't exclude the outlier and calculate a standard deviation. This is also one of the reasons why you really want to aim for more than 5 trials. It's also worth pointing out that if you're doing a rate of reaction experiment, you actually have to calculate the rate of reaction. Unlike in biology, you can't simply average your measured time taken, and according to the IB, this is still a common weakness. This mistake is particularly severe because it affects your analysis, evaluation, and conclusion sections, as your process data is fundamentally flawed, therefore significantly limiting your analysis and justification of your conclusion. So please don't make this mistake, guys, because it can contribute to a huge loss of marks. After this, you take one of your trials and do a sample calculation. Here you go through step by step and explain how you obtained your process data. First in word format and then mathematically. You'll have to do both or you will lose marks. I personally like this table format a friend of mine showed me because it is quite easy to follow. However, it consumes a lot of space, so if you are desperate for space, it may be easier to simply write the explanation and calculation in regular paragraph format. Whatever way you choose, you should present the general equation on the side and define the variables and then go through step by step. One thing to watch out for is that you use the correct standard deviation because there are 2 different types, but otherwise this is quite self-explanatory, I find. After your sample calculations for the process data table and the process data table, you also have to have sample calculations for how you derived your uncertainties. Specifically, you need sample calculations for both your absolute and percentage uncertainties. Again, you have to explain it in both word format and mathematically, otherwise you will lose marks. Personally, this was definitely one of the hardest sections, and if you check, there was actually a decimal error in one of my calculations here, which contributed to the loss of one of my communications marks. In this video, I'm not going to explain how to propagate uncertainty because that is a whole separate topic that could be an entire video. However, if you are struggling with this, I would recommend that you read the Chemistry 2nd edition by Steve Owen's Uncertainty Unit, as I found that to be quite helpful. And also, I will try and link some information below, but I'm not sure if I can find the documents anymore, but if I can, I will link those below as well. The last thing I still want to highlight about uncertainty propagation is this statement where the IB stated that the propagation of uncertainties resulting from pairing solutions or dilutions was often missing. Weaker candidates added up all uncertainties, even those not impacting final results. Keep in mind that simply adding up your uncertainties is unlikely to properly be propagating your uncertainty. So if you're unsure how to do this, go and review the chapter in the book. Following the calculations, you need a graph. This graph should exclusively present process data. You should not include raw data on any of your graphs unless you collected your data with data logging, in which case your raw data may be presented through a graph. If your data is continuous, for example, something like increasing temperatures or concentrations, you have to use a scatter plot. If your data is not continuous or discontinuous, for example, you are comparing different types of enzymes or different types of citrus fruits, you use a bar chart. Whatever your graph is, you should have your independent variable on the x-axis and your dependent variable on the y-axis. As you can see, my independent variable was temperature and my dependent variable was mean rate of reaction. Again, both axes need to include your units and in theory also your uncertainty. Note again that due to my methodology, my uncertainty was not included for the mean rate of reaction as it varied by temperature, but if your uncertainty is the same for each trial, you should mention it. By convention, you separate your units with a slash, however, some people prefer simply placing their units in a bracket. In the grand scheme of things, I honestly don't think it makes a huge difference, but it's kind of worth noting because it is convention, I guess. In terms of the axes themselves though, make sure that you have uniform increments. For example, you don't want to go from 20 Kelvin to 30 Kelvin to 40 Kelvin to 45 Kelvin. Likewise, ensure that your significant figures remain constant. According to the IB, this is apparently still a common issue, so you really want to pay close attention to this. If your measured temperature was 300.0 Kelvin, write 300.0 Kelvin, not 300 Kelvin. Writing 300 Kelvin would imply that your measurement was less precise than it actually was, which is never ever a good thing. Similarly, on the axes, don't go from 300.5 Kelvin to 301 Kelvin to 301.5 Kelvin, etc. You have to again include the 0 on the 301 increment. Whatever you do, just stay consistent with your steps, both on the graph and with your process data. You should also adjust those increments to fit your data. In my experience, Excel usually does a fairly good job at this automatically, however, you usually have to adjust the scale so that your graph is large enough. In my case, having steps of 2 Kelvin ranging from 297.0 Kelvin to 311.0 Kelvin worked best, as it placed the graph in the center of the diagram. Your graph should also include error bars, and these error bars should not be percentage uncertainty, as this is almost always wrong. Instead, this should generally be plus or minus 1 absolute uncertainty in chemistry, which you should have derived from your uncertainty propagation in your process data. I know that it's a little difficult to see on my graph here because my absolute uncertainties were almost the same for each of my trials, but note that each of these error bars is actually slightly different, as it corresponds to the absolute values mentioned in the table above. You generally don't have the exact same absolute uncertainty value for all of your trials, so generally your error bars will each have their own unique value. Also keep in mind that it's not uncommon that your uncertainty values are relatively large, since usually at the high school level your equipment substantially limits the precision of your measured values, and therefore also your final process data values. Next, you also want to include a line of best fit and justify why you chose that specific line of best fit. Usually the original line of best fit Excel produces is not appropriate, and you should definitely review your values to ensure that you are choosing the correct one. The type of line of best fit you use is determined by the R-squared value. Each line of best fit will have a different R-squared value that lies somewhere between 0 and 1. You want to choose the line of best fit with the value closest to 1, even if that does not match your expected results. As you can see here, the line of best fit with the highest R-squared value was polynomial and had an R-squared value of 0.9771. At this level of chemistry research, it's frequent that people have R-squared values much lower than 0.9, and I was honestly really surprised how close my R-squared value was to 1. Lower R-squared values are generally due to a variety of factors, including biological variation. If, for example, you are using fruits in titration experiments or biological enzymes in rate of reaction experiments. And more importantly, a lack of high quality equipment, so don't worry too much if your R-squared value is like 0.8 or something like that. That is something you can discuss in your evaluation and analysis sections, and actually makes for great content. You should, in any case, also present the equation of your graph and the R-squared value, and somewhere below the graph shortly justify why you chose that line of best fit and type of graph. As you can see, I wrote, after examining several lines of best fit, the polynomial one was ultimately chosen as it had the R-squared value closest to 1, in brackets 0.9771. A scatter plot was chosen as the data is continuous. Maybe don't copy my exact phrasing, but you should write something along those lines. It's also worth noting that if you are a physics student, you may prefer actually deriving your own lines of best fit. However, this is absolutely not necessary and may just add additional work for you and open you up to possible calculation errors that you could avoid by simply using the R-squared value to determine the appropriate line of best fit in Excel. You should also pay attention that your font size for all of the axes are a legible font size. With this, we are probably talking like 10.5 and above. In general, teachers say your graph should be half a page, and generally speaking, I would stick to that unless you're super desperate for space, but I really would not recommend making it smaller than approximately a third of a page, as this will make your graph difficult to read and could lead to a reduction of communications marks. You should also have a key for your graph and should mention somewhere that your error bars are plus or minus 1 absolute uncertainty determined in the process data. In my case, I placed the key below my graph right here. However, depending on your graph, you may be able to squeeze it in somewhere else. And also, again, don't forget, you have to have a clear and descriptive title for your graph that includes the independent and dependent variables. Next, we have statistical analysis. Technically, this is not required. However, I would strongly recommend that you do this, as it will aid in scoring highly on evaluation and will help you to evaluate your data better and draw logical conclusions that are actually founded on your data that you gathered. Many students will conclude things that they technically can't conclude without statistical analyses, so to be safe, I would definitely recommend you do this. There are a few different types of statistical analyses that you can do, including the Pearson's correlation coefficient, the t-test, the chi-square test, and the ANOVA test. There are probably others as well that may be more suitable, but these are the ones I know off the top of my head that are commonly used in Group 4 IAs. Note that you have to choose the test that is appropriate for your data, and this definitely varies by experiment. Also, just for reference, greater than 30 trials is generally considered a large sample, 15 to 30 trials is considered a small sample, 5 to 15 is considered a very small sample, and smaller than 5 trials is usually considered too small a sample to apply tests like the t-test. You also need to include sufficient explanation for the processing to be followed. This does not mean you should include a screenshot of all of your results of your ANOVA test, but you should include a short explanation of the type of test you did, the data you performed the test on, either the raw or processed data, and a summary of the results of the test. Again, please don't plagiarize, but if you do an ANOVA test, that could look something like this. A single factor 2-key HSD ANOVA test was performed on the raw data using Excel. The p-value found was 2.8 times 10 to the negative 16 with an F-critical value of 2.47717. This p-value is much smaller than 0.05, indicating that there is a significant difference in time taken to evolve 10.0 plus or minus 0.5 centimeters cubed of gas at varying temperatures plus or minus 0.5 Kelvin, while catalase and hydrogen peroxide concentrations are kept constant. Thus, the data is quite reliable and the null hypothesis is rejected. If you are doing an ANOVA test, what you have to include is the overall p-value, the F-critical value, and whether or not the null hypothesis is rejected. Moving on, we have outliers. Note that outliers are still counted towards evaluation and data analysis, but for clarity, I would recommend making this a subsection. It is very important that you don't forget to include this section because, as the IB stated, it wasn't uncommon to find very dispersed values or outliers and students ignoring them. Students are expected to identify outlying data and to critically decide how to deal with them in the processing of data. One common weakness is that some students failed to realize the collected data were within the uncertainty range and could hence not support the later interpretation. Your statistical analysis should show you what specific trials were outliers, and you then have to explain why that may be the case. To explain these outliers, you should likely refer to your qualitative observations, because if you have quality observations, you will frequently notice that the flaws you observed earlier are likely responsible for the outliers. In my case, my ANOVA test indicated the presence of 2 outliers, 310.5K trial 1 and 305.5K trial 2. I then explained the reasons why they were considered outliers from a quantitative stance, i.e. their values deviated strongly from the mean values for those temperatures. And then I explained them qualitatively by saying 310.5K trial 1 may be explained as the bung fell out of my hand while experimenting, causing the bung to be placed on the test tube with delay. This resulted in gas escaping from the test tube while the timer was still running, thus increasing the measured time taken to produce 10.0 centimeters cubed of oxygen gas, ultimately decreasing the calculated rate of reaction and hence the mean rate of reaction. Note that this statement also explains the impact the outlier had on the process data and therefore also the final value, which is something you should also mention. Keep in mind that just because your value isn't exactly what you predicted, it does not mean it's an outlier. Because of your uncertainties, there is a range in which your measured values can fall, and as long as they fall within that region, they would generally not be considered outliers. Next, we have data analysis. Note that in theory, you could combine the data analysis, statistical analysis, and conclusion, but I really wouldn't recommend you do that because, as aforementioned, separating them into separate sections aids in maintaining clarity and will help you score high marks for communications. I would start the section by first restating your hypothesis. This is probably the only thing that I would recommend repeating throughout your entire lab, and the reason for that is by restating your hypothesis, you avoid your examiner having to flip back a bunch of pages to the front of your lab, which will often automatically result in you losing a mark for communications. After this, you basically summarize your observed results. This should include references to the general trend illustrated by your graph, your error bars, the type of correlation or lack of correlation if there isn't one, and a reference to whether your results are in concordance with your hypothesis or not, and whether or not your data is reliable. Note that this simple description of your data should be included, but will not garner you high marks if it is the only type of analysis you do. After this description, you should always go into more depth about interesting things you noticed, which could, for example, include slight deviations from your hypothesis, as it did in my case, a discussion of the equation of your graph, or alternative things. What you include here really depends on your own experiment, but you should probably be referencing to your qualitative data throughout this section. Whatever you do not want to repeat the exact same information that you mentioned in the introduction or somewhere else in your lab report, but you rather want to use this section to expand upon what you've already mentioned earlier to further explain the reaction that is occurring. You also have to reference your uncertainties and really make sure you appreciate the scope of your uncertainties and the impact that they have on your results or could have had. It is not enough to simply state results and uncertainties. You have to actually interpret and explain them. For example, I explained that though attempts were made to reduce systematic error, for example by using graduated pipettes and volumetric flasks, the accuracy of measurements was limited by the precision of available equipment. Notably, most techniques used in literature employ advanced methods with higher grade equipment, such as analyzing the phosphorescent lifetime, using transmission electron microscopy, the quenched flow technique, or data logging methods, which have a higher precision and thus increased accuracy and reliability of results. Here you can see I point out that the uncertainty affected the high systematic error. I then state what probably caused the increased systematic error, namely the lack of precise equipment. And finally, I place it into the accepted scientific context by explaining other techniques that are more appropriate to use if you want more precise and reliable values. Note that these methods all focused on the techniques used for my specific reaction, and these types of details should also always focus on your specific reaction, rather than being general techniques that are frequently used across different types of experiments. The data analysis section is also a place that can help you justify your conclusion. As the IB pointed out, many students failed to correctly describe or justify their conclusions through relevant comparison to the accepted scientific context. For this part of the descriptor, students should either be making the comparison of the experimentally determined quantities to readily available literature values, or referring to whether any trends and relationships identified were in line with the accepted theory, ideally by referring back to their original background information. This statement points out two really important things to consider. Firstly, at this point, you should refer back to the scientific context of your research and its connection to the syllabus, which is often linked to things you discussed in your background information. Because I was examining the effect of varying temperature on the rate of reaction, I didn't end up calculating anything that would have a literature value, instead focusing on the general trend. I therefore mostly just referenced back to the Maxwell-Boltzmann curve and explained the shift that occurs when temperature is increased. If, however, your research question asked what the activation energy of a particular reaction was, and you ended up calculating an activation energy, or you calculated something else that has a readily available literature value, you probably wouldn't want to focus as much on the theory, but instead you would want to focus on the literature value for your specific reaction and explain what caused your value to deviate, because your value practically always deviates from the literature value. Either way, you should still mention the connection to the syllabus and the scientific context, but if you calculated the literature value, you have additional information to talk about, which is always nice. Secondly, you have to actually reference quantitative values. Some students write their entire analyses and evaluation sections without ever stating a quantitative value from either their own experimentally determined or calculated values or values from secondary sources. The problem with this is that you may be correctly describing your conclusion, however you aren't actually justifying it if you aren't referencing any quantitative values. You can't make blanket statements that have no support from your data, so just make sure you draw attention to the relevant quantitative values when necessary. After this, you have your conclusion. This should be a short paragraph that basically just answers your research question by naming the most important values. Here you have to refer back to your research question and conclude something that is fully founded on statistical analysis. For example, I could not have said that my results showed a statistically significant correlation if I had not done the ANOVA test. Also note that you can never ever accept a hypothesis. You can only reject it or support one. In general, don't be super optimistic with your results. If your results don't show a correlation, that is okay. All you have to do is explain why that could have been the case and say that further research is required. After the conclusion, you have your evaluation and improvement section. First, you state your strengths. These should be in prose format, and subsequently you note your weaknesses, which should be in a table format. Your strengths and weaknesses really do depend on the individual experiments, but a few common strengths are the wide range of data collected and affordable materials. Some common weaknesses are biological variation, fluctuation in temperatures, limited trials, and lack of precise equipment. For your table of weaknesses, you should format it something like this, where you state the weakness, talk about the impact of the weakness, and then state how you can improve it. I do believe I read something about there being a difference between the limitations and weaknesses, but I couldn't find what exactly it was, and to be honest, I don't think it will make a huge difference if you called this table of limitations or table of weaknesses, but I figured it was worth mentioning, and if one of you guys knows, please comment down below because I would be interested. It's also good to point out that the IB stated most students did succeed in identifying weaknesses and limitations calculations, although these were usually procedural, why the planned method was not properly implemented, and few were methodological, why the design method itself was flawed or limited. I would therefore recommend that you aim to have a good combination of both procedural and methodological weaknesses. At the very least, try to have one of each. Again, for the weaknesses, I encourage you to name more than are officially required, since if the IB says some of your weaknesses aren't valid, you can still score full marks. Note that you should have already referred to most of these weaknesses in your data analysis and conclusion section by discussing how they may have affected your results. You should also mention if your error was systematic or random. I honestly sucked at telling the difference between the two, so I recommend you read up about the difference, but my understanding is that random error can be balanced out by an increase in number of trials, whereas a systematic error will always remain no matter how often you measured something. For example, if you're measuring something with an imprecise tool, your results will always be imprecise no matter how often you measure it, unless you change your tool to something that is more precise. In contrast with a random error such as human rate of reaction, if you measured something 5 times, a minor change in your rate of reaction will have a large impact. Whereas if you measured something, say, like 100 times or something like that, chances are that sometimes you will react faster and other times you will react slower, so overall the error will balance out and influence the results less. Again, I'm really not that great at this though, so I really do encourage you to do your own research, especially because it was stated that the number of students identifying systematic and random error continues to be low, and quite a few did this wrongly. The same applies to the terms precision and accuracy. After this, we have a section called Future Suggestions and Implications to the Wider World. As the title of this section states, these are suggestions of future research and the implications of such research to the wider world. Note that your suggestions for future research should be somehow connected to your own investigation. For example, since I examined catalase, which is a catalyst and enzyme, I suggested investigating how the rate of reaction changes when using a variety of different enzymes. But if you were investigating something like the effect of alkane chain length on boiling point, it would, generally speaking, make very little sense for you to suggest that next you would like to investigate the effect of changing temperature on catalase activity or something like that. Note that you have to be able to conduct your suggested research with the equipment available at your school, and your future suggestion has to be an original idea and cannot just be your exact research question but using a different catalyst, for example. After this, you only have to mention your works cited and you're good! Before finishing this video, I just have a few things I want to mention regarding communications that didn't really fit into other parts of these videos. All of these were mentioned as common mistakes in either the past IB biology or chemistry subject reports, but they are fairly applicable to all Group 4 IAs. Here's basically a list of things to consider for communications. If you want to pause the video now, pause it. I would recommend reading through it. You also absolutely have to use SI units. It is not okay to use anything like pints or gallons, and if you do use these, you will immediately lose communications marks. Measuring in these units will also cause you a lot of problems because most of the chemistry equations are set up for the metric unit, and therefore if your input value doesn't match the unit that you're supposed to use, your process data will be incredibly faulty. Finally, the IB also mentioned that the number of decimal places were sometimes irregular or they did not correspond to the precision of the data. Again, this just comes back to the point that you have to be consistent with your significant figures throughout your entire IA, and especially in chemistry, this will be under scrutiny and you should really pay attention to that. A few last thoughts on hybrids and simulations. Due to COVID-19, I'm certain many of you will be forced to do database IAs using simulations or a hybrid for your chemistry IA. To be honest, I'm not very knowledgeable about using simulations as I obviously did a practical chemistry IA. However, one important thing I came across while reading the subject reports that I really want to emphasize is that you absolutely have to use data from a variety of different sources or databases. For example, my understanding is that if you're running simulations for the rate of reaction as you're changing temperature, you should find multiple different simulations or research papers and gather a variety of data. The reason for this is mostly that if you only use one database, every trial will obviously have the exact same result because your simulation is pre-programmed and generally only has one set value for each setting. When you then go into the stage of doing data analysis, you will have problems calculating uncertainties, standard deviations, etc. because all of your values are the exact same and therefore you'll have 0 for many of these values, which is not representative of reality. Finally, apparently you should also not use any closed simulations, which seems to be uncommon though, but it was pointed out so I thought I'd mention it.
Okay, so that was all of my advice on how to score a 7 on the chemistry IA. I hope this video helped you learn how to write a good chem IA and score well, and I hope you all do really amazing. And really go and read the subject reports, they're super useful. I will also link below some really good information that you can check out, and hopefully that will also be useful to you. Just have an awesome day and don't stress too hard, guys. I know it can be really exhausting, but you will get through this because a lot of others have before you and you can do it too. Just invest the energy and stay sane. Okay, bye!